welcome to the lecture about cooling cycles. And in this small lecture, I'm going to tell you about the working principles of a cooling cycle. And there will be another movie clip that will be about efficiencies and variations to cooling cycles. And there will be another lecture movie clip about heat pumps. So now I'm going to tell you about the cooling cycles. And first we need to state the objective of a cooling cycle, because it sounds rather easy. Just cool something in space, like your refrigerator or whatever. But actually it's not that easy, because it's not possible to create coldness. It's only possible, and that's the objective of a cooling cycle, is remove heat. So that's the objective of the cooling cycle, to remove heat from a certain volume. Think of your refrigerator, that's the easiest. And to do this, there's a physical principle, which is, well, really the basic principle of the working of cooling cycles. And this principle, and I'm sure you all are familiar with it, is evaporation by evaporation. So when we talk about a cooling cycle, you should think of evaporation. That's the bottom line of this lecture. So how does it work? Well, and since you're all at home now, you can probably try this experiment, and I would recommend you to do it. Get some nail polish remover, just a wee bit, a tiny drop, and put it onto your hand. And you will feel that your hand immediately starts feeling cold, and maybe and that is because of the evaporation process. The nail polish remover will directly evaporate. For this evaporation, heat from your hand is required for this evaporation. So it will extract the heat from your hand. We're going to remove heat by evaporation, and for this we need a couple of items in our cooling cycle. And there are actually 4 items in this cycle. And the first item is the evaporator. And which basically looks like this. Imagine we've got the freezing compartment, of the refrigerator, which has a spiral on top. So using of color. So over here, so there's this spiral on top. Fluid goes in and fluid comes out, or maybe it's not, fluid comes out, and during this process the fluid has evaporated. So actually a liquid goes in, so a liquid, and a mixture, or even vapor comes out. Mixture or vapor. And during this process, the fluid has extracted heat from the area. So Q in. So heat goes in to this, this spiral filled with some liquid. So that's the first, it's the most important thing of the cooling cycle. Like, the basic principle is evaporation. So, the evaporator is of course the most important part of this cycle. In order to get some fluid to actually evaporate, you need to expand this fluid like this. Maybe you've seen this or don't even done this experiment before, I have some water over here, and it's in a syringe, so air is out now. And when I cover the top of the syringe and pull the syringe, I lower the pressure, make the fluid expand, and it will start boiling. So in other words, a phase change will occur. And that's what I want to happen in my cooling cycle as well. For this I need to lower the pressure. And I can do this fairly easily by the next component of my cooling cycle, which is the throttling valve. Throttling valve. So, and as you may remember from one of the first lectures, the throttling valve looks like this. Flow goes in, flow goes out. And as you know, energy can never be lost, so my enthalpy of the flow going in is equal to the flow going out. But during the throttling valve is used for expansion of a fluid, so what will happen is the pressure that goes in is higher than the pressure going out. So the pressure will be lowered, and of course what you can imagine, if I expand the fluid and it will, well, like over here, what I just did with the syringe, entropy will increase. So the entropy in will be lower than the entropy out. So enthalpy will remain constant, so the amount of energy inside the system will remain constant, but the entropy will increase. We got the evaporator and the throttling valve now, which are the basic components used for evaporation. But we want a continuous cycle, so for this continuous cycle we need to get rid of our heat somewhere, and this can best be done by using a condenser. So I'm going to draw the condenser. Condenser. And condenser looks like this. Flow goes in, flow goes out. And here we've got a mixture, or even a superheated vapor, and out comes a liquid. And during the process of condensing, heat comes out. Q hot, out. Yeah, so heat comes out to the environment. And in the last stage, to keep everything going and to make condensing a little more efficient, a compressor will be used. So I'm going to draw this as well. So the compressor. Which looks like this. So a fluid comes in and a fluid goes out, and you have to add work to this device. And I think that's it for the compressor. So P low goes in, P high comes out. Yeah? So these are the basic components of a cooling cycle. And well, from the evaporator will absorb heat, Q in. The condenser will reject heat, so Q hot out, and for the compressor we will need to add work to the cycle. So now I'm going to combine all this to a cycle, and the cycle looks like this. So we have, I'll start with the compressor over here. After the compressor I have my condenser, and after the condenser I will have my throttling valve. There's a light bulb on my throttling valve that looks like this. Throttling valve, and over here I have my evaporator. So a flow goes from my evaporator to the turbine. Let's call this flow 1. From my turbine a flow goes to the condenser. Name flow 2. From the condenser a flow goes to the throttling valve. And from the throttling valve a flow goes to the evaporator. So 4. So this is the evaporator. Right over here. Evaporator. A turbine. And condenser. And a throttling valve. Throttling valve. And maybe this cycle is a little familiar to you, because we call this the reversed Rankine cycle. So the reversed Rankine cycle. So it goes in the reverse direction of a Rankine cycle, and instead of a turbine, it's not a turbine. This should be my compressor. So there's a compressor over here. Compressor. So we call this the reverse Rankine cycle, since the flow goes in the reverse direction. And as you may see, there's no turbine over here, but a throttling valve to lower the pressure. Okay. Well, as I'm interested in the thermodynamics principles behind the system, we're going to make a TS diagram, and since it's very useful, we're going to make a pH diagram as well. I will make the TS diagram over here, temperature, entropy, and over here I will make the pressure and enthalpy diagram. Pressure, enthalpy diagram. And in the first stage I'm going to start, before I do this, I need to draw my vapor dome. So let's draw it over here. The vapor dome, starting over here, going over there. So, and over here I'm going to draw my vapor dome as well, and it looks a bit different, since it's a different diagram, something like this. So, and draw my isobars as well, so let's assume there's one isobar over here, which looks like this, and goes up there, and there's one isobar over here, which goes like this. And of course it doesn't make any sense to draw the isobars in a pH diagram, since these will be straight lines. So now I'm going to draw what happens in my first, well, from stage 1 till 2, and I write down over here what happens as well, 1 till 2, and I'm assuming that the compressor I'm using is isentropic, just for this example. So the first stage is isentropic compression. So in the evaporator we made mixture, or even in some cases a saturated vapor, but now we're going to assume that we just have a vapor. So over here we can choose more color, better visibility. So stage 1 over here, and we're going to stage 2, isentropic, and straight to the top. So this is stage 1, stage 2. And in this diagram it will look like this. From 1 isobar, so point 1, at the vapor dome, in the vapor region, I'm going to increase the enthalpy by a compressor to over here. So, and I've increased my pressure. So in the second stage, I'm going to get rid of all of the heat at a constant pressure. So let's call it stage 2 till 3. And that is isobaric heat rejection. So I'm going to get rid of all the heat. Draw it again in my line, and I'm going to withdraw, to reject heat until I reached my liquid line. So like this. So, and here is point 3, and over here it looks like this. So just the enthalpy decreases until we're at the liquid point. So 3. So over here I reject the heat. From then I'm going to stage 4, so 3 till 4, and this is isentropic throttling. So I will reduce the pressure at a constant enthalpy. So isentropic throttling, and that happens like this. So remember, constant enthalpy, but entropy increases, so it happens like this. 3 till 4. And over here we have a constant entropy, so we should end up here. So this looks like this. It's a straight line. 4. So isentropic throttling. And then in the last stage, so 4 to 1, 4 till 1, we have isobaric heat addition. Isobaric heat addition. So heat is added from the system. So actually heat is extracted from the system, and phase change is going on. So the phase change is not really a phase change. It will still remain a mixture, but the more vapor will be in the mixture. So the mixture will change, and over here as well. Okay. So there are a couple of items I need to mention over here, because in this, at the compressor, we have to add work in. So that happens here as well. Work in. And it happens over here as well. Work in. Here we're getting rid of all of our heat. So Q hot out. So rejecting all the heat. That happens here as well. Q hot out. And it happens here as well. Q hot out. And over here, and this is actually the most important step in which we are really interested. Q, let's make it a little longer, Q cold in. So it's a lower temperature and heat is added to the cycle. That happens here as well. So Q cold in, and here in the evaporator Q cold in. Now, so this is basically the description of the cycle in a TSPH and of course our schematic diagram, and these are the stages the cycle is going through. There's one thing that needs to be mentioned, and that's about the working fluid. And the working fluid is usually a fluid which evaporates quite easily at this lower temperature. So, for instance, refrigerant 134A is used, but in the industrial processes, different liquids, fluids are used for the refrigeration side. Just to make sure you understand what's happening when you cool your drinks, I will make a schematic drawing of a refrigerator in the middle. So this will be my refrigerator, and we're looking to the side of this refrigerator, so it's a side view. So like this. So here I got my refrigerator, and in the bottom of my refrigerator there will be the pump or the compressor. So compressor. And this compressor basically looks like this. Maybe you've seen it before. It's from my fridge, which isn't a fridge anymore. And from my compressor, the flow is going into the condenser. And the condenser is not like a pot with liquid and a mixture, but it's like a spiral tube at the back of your refrigerator. Maybe you've seen it. And after that, so this is the condenser. And so the refrigerant, the liquid that's inside the cooling device, the refrigerator, cools by natural convection and conduction to the air, outside air. So over here I've got my throttling valve, and in refrigerators this is a capillary tube throttling valve, or even just a valve. And after that it goes into my evaporator, which is basically another spiral tube over here. After that, flow goes back into my compressor. So this part over here is the evaporator. So it's mounted on the top side, on the top of your refrigerator. So I hope you think of this when you're getting your next drink out of your refrigerator, and of course keep the reverse Rankine cycle in mind. Good luck with the assignments, and see you in the next movie about efficiency of the reverse Rankine cycle. Thank you.